Hey, did you think you were finished lesson 9? So did I. Sorry about that. Hopefully you are watching this and hopefully you watched it after because you noticed then it was linked on D2L as lesson 9 part 1 and part 2, even though I made it sound like you were finished after part 1. Okay, so continuing on with lesson 9, we have example number 2. Without using a graphing calculator, make a rough sketch of the graph f of x equals negative x minus 1 to the fourth, and x minus 4. Okay, there's our factors. Verify with the graphing calculator. Okay, so let's see here. Rough sketch of the graph. Let's first find our zeros, okay? So to find our zeros, or x-intercepts, we're going to set each factor equal to 0. Now, you're probably already ahead of me thinking, oh, well, they're x equals 1, right? Set x minus 1 equal to 0, and x equals 4. But there's one here you probably didn't notice. It's the sneaky one. X is also a factor, okay? So we also have an x-intercept or a 0 of this function of x equals 0. So we have three distinct zeros. Okay, so let's put them on our graph as x-intercepts. So 0, 1, and 4. Okay, now to graph this, we have to look at our leading coefficient. Okay, so imagine if this was all expanded, we'd have a negative 1 times our x, and then this would end up being x to the 4. It would be one of the things, and then this would also be x. So if we multiply that out, we should have negative x to the 6th as our leading term, or our highest degree term. The coefficient, therefore, the leading coefficient, is equal to negative 1. So negative in particular. So if the leading coefficient is less than 0 or negative, our graph needs to end down. So that's how we know where to start drawing this graph, is we start by drawing a little arrow ending down here. Then we're actually going to draw from right to left, which I know is weird, but from right to left. And each time we approach an x-intercept, we have to look at how it's going to behave based on the multiplicities. So x equals 0 had a multiplicity of, well, the exponent is just a 1 on that, so a multiplicity of 1. So it should pass straight through at that location on the x-axis. This one, x equals 1, had a multiplicity of 4. Okay, so an even multiplicity means it's going to bounce off of or is tangent to the graph at x equals 1. And this one had a multiplicity of 1. So it'll pass straight through. So the one we're heading for right now is x equals 4, which has a multiplicity of 1. So we're going to pass straight through. Okay, how high it goes doesn't really matter as long as you've got the behavior of the graph correct at each of these locations. So don't put any extra twists or turns in it. Okay, now at 1 we have to come down and bounce off of or become tangent to. So I'm going to go like that, and don't go too high back up because we have to go back through at 0 like that. Okay, it's a rough sketch, but that's okay. So we're going to verify that with the graphing calculator. So grab that, throw your equation into y1, and let's take a look at the graph. Okay, so we have that equation put into y1, and we're going to take a look at the graph. I'm going to set our windows back to zoom standard, and then we'll adjust accordingly, but there we go. Now we can't see the top part of the graph here. I'm not sure that's a big problem because we're more concerned with how it's behaving around the x-intercepts. So yeah, you notice that we on ours put a little bounce here, and I'm not seeing that at all here. So it's because there's not much of a bounce. So you know what, let's actually zoom in at that location and see. So we'll just go a little bit to the right. We know that's happening at x equals 1. So let's zoom in there and see what's going on there. Ah, see, now we can see it, can't we? Okay, so it does go through x equals 0, comes up a little bit, and then it bounces off of x equals 1. Okay, so our graph then was pretty good here. Obviously, it went much higher here, right? But that's okay. We've got what we need. All right, so Example number 3. The following graphs represent polynomial functions p of x of lowest possible degree. So that means if you had a choice of a multiplicity of 3, 5, 7, or 9, you'd choose 3. All right, so for each, state the degree of the polynomial function. And for p of x equals 0, okay, so the x-intercepts, or zeros, state the points on the graph which represent real and equal roots. Okay, let's do the first part. State the degree of the polynomial function. Well, the degree is the same as the sum of the multiplicities of each of the zeros. Okay, so let's go through and write down the lowest possible multiplicity for each one because they want lowest possible degree. So the lowest one it bounces off would be multiplicity of 2. Passes straight through, that would be a multiplicity of 1. I'll just go m of 2, m of 1, meaning multiplicity. And this again would be a multiplicity of 1 because it passes straight through. So adding those up, 2 plus 1 plus 1, we should have a degree, lowest degree, of 4. Okay, for p of x equals 0, state the points on the graph which represent real and equal roots. Well, the equal roots happen when the graph either is tangent to or it snakes through. So that would occur at A. State the points on the graph. So point A would have 2, possibly, real and equal roots. Okay? All right. Why don't you guys try graph B, and then we'll check and see if we have the same answers. Okay? Pause your video, please. Okay, so for graph B, we should have had a multiplicity, lowest possible, of 3 at point P, and again, also 3 at point S, because the graphs snake through those points. Okay, so our lowest possible degree would be 3 plus 3, which is 6. Okay, so where would we have real and equal roots happening? At both point P and point S. Now, did anybody get suckered in on the y-intercept there, thinking that that was actually a 0? Please don't do that, okay? Only x-intercepts are zeros. Okay, example number 4. On the grid, sketch a graph of the polynomial function satisfying the given conditions. Okay, so they want positive lead coefficienting. That means it ends up in quadrant 1, so it's going to end up here. So we can draw a little arrow there. One real 0 of multiplicity 1, so we have to cross straight through at 1 x-intercept. 2 real zeros of multiplicity 2, so we have to bounce. And of 5, that's an odd multiplicity, we have to snake through or have a point of inflection. Okay, so tangent, point of inflection, and then we also have cross straight through. All right, so let's do cross straight through, tangent, and then a point of inflection, and there we go. Okay, not pretty, but it works. All right, why don't you guys try the second one, negative lead coefficient, all that stuff, and we'll see. We won't have exactly the same graph, but as long as you satisfy these conditions, we'll be okay. Okay, so pause your video, and you guys try that second graph. Okay, so ends in quadrant 4 because of the negative lead coefficient. Oh, and I drew the quadrants up here too, in case you've forgotten what the names are, quadrant 1, 2, 3, and 4. Okay, so ends down in quadrant 4. We have 2 x-intercepts where it passes straight through. So we can get those out of the way first if you like. Then we have 1 snake. They don't have to be in order like I'm doing them. 1 snake, and then 1 bounce. And there we go. That would be a possible graph. As long as you have satisfied the bounce, the snake, and 2 straight throughs, your graph is fine. Okay? State the degree of each polynomial function. So we're adding up the multiplicities. So the sum of the multiplicities would give us that. Okay? So for the first graph, we would have 1 plus 2 plus 5. So our degree would equal 7. Oh, sorry, 8. Great. I can't add 1 plus 2 plus 5. Good job. Okay. Pause your video. You guys come up with the degree for the second one. Okay, and did you get a degree of 8? Are you guys really pausing that video? Anyways, okay, degree of 8. Good job. Let's take a look at the next page and finish up this lesson. Okay, so we're going to investigate some non-real zeros. Okay, now non-real happens when we try to square root a negative number. Okay, now you are not expected to know how to calculate these non-real zeros, but you are, because it's not really an extension, you are expected to know where on the graph they would occur. So like what situation would give you non-real zeros? And we'll talk about that on the next example. But for this one, we're going to investigate how that happens. So they took this polynomial, this fourth degree or quartic polynomial, and they factored it, and they got these three factors. Now this one looks like it's not quite done yet, but, oh, and first they want us to state the two real zeros that have a multiplicity of 1, so they're referring to these two. So that would be x equals 2, right? Because we go x minus 2 equals 0, solve for x. And the other one would be x equals negative 3. Great. Now, to find the other two zeros, because with degree 4, we should have 4 zeros. Solve the equation, even if some of them are equal, right? Solve the equation, yada yada, using the quadratic formula. Okay, so remember quadratic formula, negative b plus or minus, yada yada. Okay, and our a value is going to be 1, the coefficient in front of x squared. B will equal negative 1, and c will equal 2. Okay, so we're going to put those in, and I'm going to do that and then simplify it, and you do that as well, and we'll see if we get the same thing. Pause your video, please. Okay, so we should have gotten to this step here, and then you went, uh-oh, I did something wrong. I'm trying to square root negative 7. Well, no, you didn't do anything wrong. What happens is this will give us non-real answers or imaginary values. And as a result, then, we wouldn't have any actual x-intercepts for those two zeros. So they talk about how the two zeros would be 1 minus the root of negative 7 over 2 and positive. Okay, now what we're going to do is we're going to see how those show up by graphing this equation in our graphing calculator. Set your windows to this, and then and you're going to pause your video to do that, and we'll make sure we have the same graph showing up, okay? And we'll talk about where these zeros are showing up on our graph. Okay, let's pause the video. Okay, so you've got this equation in y1. From there, we've set our windows to what they've said, x min, x max, x scale, yada yada. And now let's take a look at our graph. Okay, there's our graph. Well, here's our x-intercept of negative 3 that we got from here. Here's our x-intercept of 2 from our other real 0. And what's happening is you'll notice that the graph has a little kind of change in concavity here, doesn't it? It goes from concave up here to concave down here. All right, well, when it has a little in the graph there, that shows up as non-real zeros. Okay, so that's where that is occurring, is in this area. Okay, it's nothing to do with the y-intercept. Please don't, it just happens to happen in that area. Here's actually the point of inflection would be right here. Okay, so let's go back to our thing here. If a real polynomial function has non-real zeros, then non-real zeros always occur in pairs, which are conjugates of each other. Okay, and you saw that from up here. That looks like glasses. Okay, I digress. All right, so where q is less than 0, because to get non-real, you have to be square rooting a negative. And these are imaginary zeros or complex zeros when the real part of it is thrown in. Okay, let's look at these graphs and see which would have non-real zeros. Indicate the region on the graph that would represent the non-real zeros, and then write a statement about the number, type, and multiplicities of these zeros. Okay, so I'll walk you through the first one. This would be a real 0. Okay, one real 0. Okay, we've got a little bounce in the graph here. Okay, so that would be 2 non-real zeros. Okay, now this should be degree 3 because we have 3 direction changes. 1, 2, and 3. Okay, why don't you guys try these 3? I'm hoping to finish this before it runs out, but it looks like we're not going to. So we will continue this in a very short video, part 3, lesson 9.